the microphone well? Yeah, you can hear me also in the back? Not good. Better now? Okay. So if you cannot hear me because the microphone goes up and down, make me a sign or something and I try to remedy. Okay, so good morning. Welcome to the second week of this workshop. I think I do not need to introduce myself because you might remember from last week that I've already been here and telling you some other stuff. So today's day is dedicated altogether to electronic excitations and various ways how this can be calculated. So this first talk here will be an introduction to time-dependent density functional theory and the particular way how density functional theory is being solved or can be solved with the ways we have implemented in quantum espresso. You will see this later. Then the other part of today's electronic excitation lectures are dedicated to many-body perturbation theory, and there you will hear about so-called GW and Bethe-Salpeter methods and so on. And in the afternoon, obviously, all this will be done with hands-on sessions together. So now, since I'm the first one and I'm starting off all this, let me say some words about electronic excitations in general, and the question why we need these different approaches. Why do we need time-dependent density functional theory and many-body perturbation theory? So what is the difference and why are we doing all these kind of things? Okay. So since last week, you have already been extensively using density functional theory and quantum espresso for all kinds of things, from molecular dynamics to ground states and so on. I think all of you have seen this kind of piece of an output of a typical quantum espresso calculation. So the code iterates and iterates in any system you would like to have, and then in the end, when it has reached self-consistency, it tells you the number of k points, in this case just one, k point 0, and a whole series of energy eigenvalues. And then the code tells you, obviously, the most important thing, which is the total energy. And the total energy obviously refers to the energy of your system in the ground state, because quantum espresso is a density functional theory code. So this is density functional theory, a ground state theory, and one ends up with a given total energy. However, you have also these eigenvalues, which I've just alluded to. And in this case, the code also tells you the highest occupied and lowest unoccupied levels are these here, -8 and -1. So if you look at these here, then you see, okay, all these Kohn-Sham states up to this one here will be doubly occupied, and these here will be the empty ones. So in principle, one can say, very nice, we have already electronic excitations, because all which we would now need to do in order to excite the system, go away from the ground state, is take some electron from one of these occupied levels and put it into one of the unoccupied levels. Okay? So this is kind of the first thing which someone might do. Okay, so instead of having all electrons in the lowest state, so I take the lowest states, each one 2 electrons, and this is obviously the lowest energy I can obtain. I will now try to do something better and put 1 electron to up or 2 and so on, and one gets all kinds of excitations. Now, doing this is something which is not allowed, and in fact would be quite wrong. Not because the concept of having energy levels which are doubly occupied and from which you can take electrons out would be wrong, but because density functional theory has not been created to do this kind of approach. Okay? So the fact that in density functional theory you end up with the Kohn-Sham Hamiltonian, which has eigenvalues, in fact these here are the eigenvalues of the Kohn-Sham Hamiltonian, this does not mean in any sense that this approach has been created to solve electronic excitations. Okay? So in a sense, if you want, these virtual states or the energy values which you find here are not the ones which are supposed to give you energy excitation. So the difference between -8.8 and -1.8 is not supposed to be really a kind of an energy which you need to furnish to your system to promote 1 electron up. So while this is something which, so on one hand it's a mistake, you must not do it, it has not been created to do like this, DFT, still this idea of having kind of levels which look like single particle levels in a many electron system, this is not a bad idea. So this whole concept that one tries to understand a many electron system, like so the molecules or the crystal which we are looking at, and try to understand what happens to the electrons in terms of promoting a single electron away from where it is in the ground state, this is a good idea, because it has been shown over and over again that this idea that even though the wave function for our electrons is in principle many electron wave functions, one can very often very well describe excitations by the idea of having just a single electron or perhaps two electrons being promoted from some so-called, from some energy states to some other ones, okay? So this concept that in principle one can very well describe excitation properties of an electronic systems in terms of single particle properties. This is often called a quasi-particle concept, and this is a concept which is very good and holds very often very well. But there are also notable failures where with the single excitations you cannot describe at all what is happening to the electronic excitations. But in principle, so this concept, you should distinguish, first of all, this idea that yes, one can have this single particle image of what happens in electronic excitation, and one can very well distinguish this from the fact that the Kohn-Sham energies are not the ones you should use for doing these kinds of things, okay? So here I also tried to show you something. These kind of pictures is what you see typically in chemistry or when you talk about molecules or small clusters. Why so? Because there you have single energy levels, like the ones I've shown you before, between which you can excite the electrons. If you go to extended systems, so crystals or whatever it is which has infinite periodicity in 1, 2, or 3 dimensions, you will end up with bands. This we have also seen last week several times, where you have k vectors, and instead of having these single particle levels with a HOMO and a LUMO, you will have whole bands, and the story is exactly the same. Some bands will be completely doubly occupied, and others will be empty bands, and also here we have this concept of quasi-particles to be able to promote electrons. So this, however, is not all. And when one talks about electronic excitation, so the concept of kind of a single particle picture is often a good one. But I've noticed when one talks to students and so on, there's often a confusion about which kind of spectroscopy and which kind of property is one looking at. And the very important distinction between everything which we will hear also today is between this concept of so-called charged excitations versus neutral excitations. So what are these? We've said, well, we know what the ground state is. All electrons are doubly occupying some low-lying states. And a charged excitation is an excitation where you take this kind of system and you add one electron or you remove one electron, okay? So imagine you have, for example, a molecule. Everything is in the ground state, all levels twice occupied. And now, with some kind of experimental probe, you are able to either rip off an electron or you are able to add an electron to the system, okay? So these are called charged excitation because you can in principle imagine that the system with n electrons is an overall neutral, for example, molecule, and then you go to a charged one which has one charge more or one charge less. The place where you're going to put, for example, the additional electron which you are putting in here is not necessarily the electronic state which gives you the lowest energy. In that case, you would simply have, again, the ground state of an n+1 electron system, which is a special case. In principle, there are many other places where you can put the additional electron, and there are many places from where you can take away an electron if you are going to the n-1. So this is one kind of experimental probe which leads to charged excitations. And one should very clearly distinguish, for physical reasons, these kind of excitations from so-called neutral excitations. In a neutral excitation, you remain with the same number of electrons before and after your experimental probe, okay? So for example, you might here have a band which is completely filled, and then a neutral excitation might take one electron, not necessarily, as it is shown here, the highest energy electron, but some electron out of your system and put it into another state. So the total number of electrons remains the same. However, you now are not in the configuration which has the lowest energy. I'm insisting on this distinction between charged and neutral excitations because the computational tools you will need to approach these two kinds of systems are completely different, as I will kind of say in a minute. So why are they physically so different? Well, if you are trying to approach from a computational point of view such a system where you have a charged excitation, then you can see that basically all you have is electron-electron interactions, like as if you had calculated, in fact, a ground state. So you have in this case, n+1 electrons, and all the electrons interact with each other, also with the extra electron, and you have all these electron-electron interactions. The case is different if you are considering neutral excitations, because in neutral excitations you have obviously electron-electron interactions between all the electrons which are in the system, but this electron, which has been in this case, for example, gone up from a filled state towards an empty state, leaves behind this so-called hole, okay? And you can imagine, so this hole, if you want, you can consider it as a positive charge, while the electron will be a negative charge. And obviously, this positive and negative charge, they will interact. So in a neutral excitation, you have to somehow be able to correctly describe the electron-hole interaction. And this electron-hole interaction, which is generally an attractive interaction, it can be very strong, okay? So in this sense, calculating neutral excitations is more difficult and more involved, because not only you have to be able to describe all the electron-electron interactions, but somehow also the two-body problem of an electron-hole interaction between excited electron and the hole which has been left behind. How are these things measured? Well, it has already been written on the previous slides. If you add or remove an electron, this is typically done in the way that you have a sample, and you shoot electrons on this system, and then you have either photoemission spectroscopies, where you have a sample, an electron comes in, and a photon comes in, and you shoot out an electron. Or you can have a so-called inverse photoemission experiment, where you have an electron which stays in there. So you have photoemission or inverse photoemission, which allows you to go from n to n-1 and n+1. These are the typical kind of experiments, where the typical kind of experiments for neutral excitations is optical spectroscopy. Because in optical spectroscopy, you just shoot with a photon on your system. The electrons all remain in your system, in your sample, but you are measuring at which frequency you get an absorption of your light and which frequency you do not get absorption, and this is a typical case for these neutral things. So when you're talking about optical properties, so you are wondering which is the color of a given material or something, then you are interested in in neutral excitations, because the number of electrons remains the same. The electron will go to some excited state, and in order to calculate this, you will need to somehow take care also of the electron-hole interaction. Okay? Now, let me say some words about now time-dependent density function theory versus many-body approaches. On one hand, it is clear that, and this will the whole day be explained more in detail, when you should use one, when you should use the other. Here at 9 o'clock in the morning, let me just say some very, very general approaches. So when one speaks about many-body perturbation theory, one normally refers in this context first to the GW approximation. So you will hear in a later talk, or the formalism, how the GW approximation works. But kind of to imagine what is really being done is, if you do a GW, what you obtain is the bands, either the bands or the energy levels, but you obtain the right ones, not the Kohn-Sham energy levels, those which are filled and those which are empty, which I said in the very first slide, are not the ones you take. You obtain the right energy levels for the quasi-particles, okay? So the GW approximation gives you, for a charged excitation, the right levels, the ionization potential, the electron affinity, and so on, and all these kind of levels where you can either put an extra electron or you can remove an electron from. What is missing in the GW approximation is what you need for a neutral excitation. It's the electron-hole interaction. Okay? So if you are interested in optical properties in this many-body perturbation theory context, then you will have to add to having the right energy bands for the single particle excitation, you will have to add electron-hole interaction. And this is typically done solving an equation which is called the Bethe-Salpeter equation. And the Bethe-Salpeter equation is kind of a more difficult equation because it's a two-body equation which solves you precisely what I've said before, the interactions between an electron and a hole. Okay? So the idea is you get the right energy levels for charged excitation using GW. On top of it, you solve a second equation for the two-body problem if you want to solve neutral excitations. How all this works comes in the next talk. This is not the topic here. Now, how does this kind of framework, which I've just said, refer to time-dependent density function theory? Well, in time dependency functional theory is a method which is made for neutral excitation directly. So it does not give you a correction to the energy bands, or it's not a method which solves you, kind of, gives you a band structure better than the Sham band structure, but it is a method which goes, I will show you later all the formalism, but just to get the mind ready, it is a method done for neutral excitation which directly solves for electrons which do not stay in their ground state, but they move around in the system and go towards higher excited states. So in principle, time-dependent density functional theory is a method for neutral excitation, and it directly contains, if done exactly, all the electron-hole interaction and things which you might need. Okay? So the question is, when should one use which? Okay? Also here, you can do a whole PhD about finding out when it is better to use what. Here I will just show you some very quick and dirty rules of thumb. Okay? So you should first distinguish if you are looking at an isolated system or if a solid, say, extended system. As a very rough rule of thumb, if you're in an extended system, say a silicon crystal or something like this, you will essentially be lost if you try to do TD-DFT. Why so? Not because TD-DFT could not do this, but because the functionals we have at our availability, they are not good enough to describe excitonic effects, meaning the electron-hole interaction in an extended system. If you try to calculate the absorption spectra of a bunch of silicon, it will get completely wrong with the usual adiabatic LDA or adiabatic GGA functionals which we are using. I will say later something about these functionals and which functions we are using and how it goes in TD-DFT, but just starting off, should keep in mind that, so it's not always true that TD-DFT is bad for solids, but the usual functions are often not adequate for solids. This can obviously be remedied, so if you use more complicated functionals, people say that, for example, if you use some range-separated hybrid functionals, then it might be good and so on. But as a rule of thumb, most people, when they say TD-DFT, they think about adiabatic GGA, adiabatic LDA, and then typically it goes wrong in most of the cases where excitonic effects are important. In isolated systems, so in molecules in the typical chemistry domain, very often even easy functionals in TD-DFT go quite well. Okay? So today, if you look at the literature, in most cases, when people try to understand what are the optical properties, for example, of a new kind of a perovskite solar cell material and so on, it's an extended system. Everyone is doing GW, beta salpeter, and so on. No one would be doing standard TD-DFT. If people are looking at some new molecules, which people are putting, for example, on some dye-sensitized solar cells, then these molecules are very often approached with time-dependent density functional theory just because it can be very efficient and very fast. Okay? So this is just a very general idea. So this was kind of the idea. We have neutral excitation, we have charge excitation, we have different approaches, many-body theory, GW, and beta salpeter, which do not come from a density functional kind of framework. And we have time-dependent density functional theory, which is clearly an extension of density functional theory, as you've seen last week. So, kind of having said all these things, let me now try to explain a little bit more in detail what this time-dependent DFT is and how it relates to ground state density functional theory. So last week already, we have seen that already in 1964, the formal ground was laid for density functional theory. Okay. And you might remember, you have seen that it has been shown that there is a one-to-one correspondence between the potential and the density. And in fact, one can use, therefore, the electron density alone in order to describe your many-body electronic system, but everything is in the ground state. 20 years later, up here it goes, in 1984, Runge and Gross have generalized this Hohenberg and Kohn theorem towards systems which are not in their ground state. And without giving all the details, the basic idea is the following. Imagine that you know of a system in which state it is at some beginning. For example, imagine you know the system which is in its ground state at some infinitely far away in the past. And then what you are interested in is what happens if you do not try to calculate its ground state for all times, but if you now perturb the system with some time-dependent, whatever potential, you might shoot some light on it, or you do something which depends on time to your system. Clearly, the electrons will react to this. And this Runge and Gross theorem, it tells you that if you have a well-defined initial state. Then a time-dependent perturbation leads, obviously, to the fact that the charge density of your system will change with time. And you have in the time domain also a one-to-one correspondence between the potential and the density. So, in fact, this Runge-Gross theorem is really a generalization, a direct generalization of what Hohenberg and Kohn have said in the time-independent or ground state case. And if you now imagine that something becomes time-dependent, so the charge density will vary with time and so on, you can clearly see that this is something which goes away from just having doubly occupied ground states, but somehow the electrons will have to move away from what is that, and this allows that one in a way which I will make clear in the following, how one can go to excited states. So both of these things, Hohenberg-Kohn and Runge-Gross, they are theorems, which means they are exact. So in principle, all these things which I've said in the beginning, be careful with TD-DFT in extended system and so on, it is wrong. So TD-DFT can describe all this in an exact way. The problem is, like in the ground state, we do not know the functional. And this problem that we do not know the exact functional, or we do not even know an appropriate functional very often, is much worse in the excited state case than it is in the ground state. While already in the ground state, there are many cases, you have seen last week talks, where one has to use GGA plus U in order to get strong correlations, or one has to do, I mean, also we have self-interaction errors and so on. So in the ground state, there are already many well-known problems. These problems become much worse if one tries to do TD-DFT and tries to some very easy approximations to the functional. So formally, TD-DF exact, but we have some issues with the functional, which I will try to make clear in the following. Okay? So, in order to explain you a little bit the formalism behind this Runge-Gross theorem, let us remember how this basic quantity of density functional theory, which is the charge density, how this is in practice handled. So you remember we have seen the Kohn-Sham framework, where one essentially makes a change of variables, and the independent variables become these Kohn-Sham orbitals, and the charge density is written as the sum of the square moduli of these Kohn-Sham orbitals. Each one of the Kohn-Sham orbitals in the ground state satisfies a time-independent Schrödinger equation, which contains a kinetic operator, then this local Kohn-Sham potential, which contains the external part, the Hartree and the exchange correlation part. And so we solve the time-independent Schrödinger equation, and we obtain the phis. From the phis, we get the density. With the density, we obtain a new Kohn-Sham potential, and so on. So this is exactly what you've seen for the ground state last week. And now, in the time-dependent systems, as I've said, there is this proof that one can also here use the potential and the density instead of the many-body wave function. So I will not, don't worry, I will not show you the proof also because it is really kind of a bit cumbersome, much more cumbersome than the proof of the Hohenberg-Kohn theorem, which one can show in a few lines. But I would like to give you a little bit of flavor of what has been done to bring this to the time domain. Okay? So the idea is, as I've already alluded to, that at some initial time, which you can imagine very far back in the past, you know the system state. And you know the many-body wave function at some initial time t0. And one imagines that one has two different quantum systems, one which I call psi, and the other one where I call everything with a prime. So you have, at the initial time t0, we imagine that these two systems are identical, or are in the same state. Okay? So our system, described by psi, has the same many-body wave function like our prime system at the initial time t0, and these two systems do not differ at that moment. Now we imagine that if we know that the many-body wave function at this initial time is the same, then obviously all derived quantities must be exactly the same. So the density unprimed and the density with the prime at the initial time must be the same, and all currents which might be flowing in this system, the electron currents, obviously they will also be the same in the primed and unprimed systems. And now we make a difference between these two systems. We imagine that at t0 they are all in the same many-body state. But now, following t0, we apply two different time-dependent potentials to the system with the prime and without the prime. Okay? And what Runge and Gross have proven is that if you have two different potentials v and v prime after some initial time, And in fact, they must really be different. It's not just that they can differ by a constant. So they must be clearly different potentials and differ by more than simply a constant. Then they've shown always you will see in later times that the current density, the electronic currents J and J prime, which you calculate for the two different systems separately, they will be different. So this is part one of the proof, that having two different potentials at later time leads to two different currents always, and you can never have the same current if you have two different potentials. So this is really the core of the Runge and Cross theorem. The second part is a much easier part, where they show that, in fact, if you have two different electronic currents in your system, then this will lead also to two different densities. Okay? So this is basically, I do not show you the proof how it is done exactly, but in principle, so they have therefore shown that if you have two different potentials, this means you will have at later times also two different electronic densities. And this establishes, in fact, the fact that you have, like in the ground state, a one-to-one correspondence. You do not need to, at all times, describe your system with a many-body wave function, but you can describe it with a charge density because of this fact that there is this one-to-one correspondence. So, as I've said, I will not go very much into the proof, but what I will show you is how this generalization of the theorem leads then to a generalization of what one does in practice. I've just shown you in the ground state case, what one does is solving a time-independent Schrödinger equation for these fictitious Kohn-Sham orbitals. And now, in the time-dependent case, one obtains basically the same thing. One writes a Schrödinger equation, however, now a time-dependent Schrödinger equation. Can you still hear me? I have the impression that the microphone is not working. You can hear me? Also? Okay. So one writes now a time-dependent Schrödinger equation for these Kohn-Sham orbitals. So essentially, the time derivative of each time-dependent Kohn-Sham orbital is given by h times phi, and h is again a Kohn-Sham Hamiltonian, which contains external potential, which will be time-dependent, but also Hartree potential and exchange correlation potential. All of them will be time-dependent because the density is time-dependent. So it looks very much like the ground state case, the difference being that one is solving time-dependent equations. So I've already said that the Kohn-Sham Hamiltonian formula looks the same. At each moment in time, one calculates the time-dependent charge density by calculating again the sum over the square moduli of these single particle orbitals. The Kohn-Sham orbitals depending on time, the density will be time-dependent. With the time-dependent density, obviously, your potential becomes time-dependent. All this would be nice and exact if it wasn't for, again, the exchange correlation part. And why is this exchange correlation part now so much more complicated? In the ground state, you know that one is trying, or the first steps towards density functional theory in the ground state have been to try to find local approximations. So the first thing which has been used was the so-called local density approximation, where you took the density at a given point, and then one is integrating over all space with an integration kernel, which at a given point in space tells you as a function of what is the density there, what will be the local exchange correlation energy density. And one takes that from an uniform electron gas. So the same kind of problem applies in the time-dependent case now. However, you not only have to be able to say that, yes, you need a local approximation or non-local approximation, which might or might not be appropriate, like in the ground state. The problem is also at a given time t, where you want to calculate the exchange correlation potential of your system. In principle, this potential will not only depend on the density at that very moment, but it will depend on the whole previous history of densities. Okay? So at time minus infinity, you might be in the ground state. Okay? And then you have evolved until time t with all kinds of oscillations, with light and all perturbations you can imagine doing to your system. And the Kohn-Sham potential you will have to apply to your system and add into the Hamiltonian at a time t will depend on the whole history, in principle, on the whole history of your densities. Okay? So you not only have local versus non-local and all these approximations, but you have also in time, local versus non-local in time. And this gives a whole new set of problems which might arise. Saying that something is local or non-local in time It tells you if you try to work in Fourier space, and instead of the time domain, you decide to work in the frequency domain. This goes under this title of finding functionals or approximations which depend on frequency. It's kind of the same story that you try, people try to make better approximations for the Kohn-Sham potential by using frequency-dependent kernels. This is nothing else but saying that somehow one tries to incorporate the time domain in these approximations. Having said this, so in principle we know that we have to take care also of the whole history of our densities. In most of the calculations, this is not done. So what one is doing is one is using a so-called adiabatic approximation. Adiabatic approximation means that we calculate at the time t the Kohn-Sham potential from the density we have at the time t. So we neglect all the previous history of the density, and we try to find some approximations. And the easiest thing, obviously, is not only to do the adiabatic, but then when you need a potential for a given density, one uses, for example, the same kind of approximations one has already in the ground state. So people use adiabatic LDA, adiabatic GGA, adiabatic PBE, whatever you want. And then people also use adiabatic hybrid functions. So you can imagine all kinds of things. So if you put adiabatic in front of any of the functionals, this means you're using the same functional form of a functional in time-dependent density functional theory. Sometimes it works extremely well. I will show you some cases. Sometimes it works really very, very poorly. And it is, like local approximations, it is a reason for errors. Okay? Is this clear so far? Okay. So in TD-DFT, we are trying to go to the time domain. We have an exact function. We have an exact theory, but we do not know the functional. And the functional is even more complicated due to this history fact, which one should try to incorporate. Let me now show you a little bit how people have been using TD-DFT over time. The funny thing is that TD-DFT is really formulated in the time domain, just as I've shown you. Runge-Gross, they've proven everything in the time domain. But nearly nobody, no, I would not say nobody, but very few people are in fact using TD-DFT in the time domain. Everyone is using, or say 90% of the papers you will find, people are using TD-DFT in the frequency domain. Not the functional approximation, but the way the equations are solved. I will show you in a minute how it is done. But very few people are really going to the time domain, which I find sad, because for someone who is trying to understand what TD-DFT is all about, it is very nice to stay for a moment in the real time domain. And this is how I will show you in the beginning how TD-DFT works. Okay? So this was done, according to my knowledge, for the first time. TD-DFT in real time was used in 1996 by Birch. And this idea of how to do it was 5 years later introduced in this Octopus code, which exists today. Today it's much more than it was in the beginning. In 2001, it was just one code which could solve the TD-DFT equations in real time. And how does it work? Okay? So it works in the following way. One does a standard density functional theory calculation of a system and calculates the ground state as you've done it last week. Then one considers that this system now gets perturbed, and one adds a perturbation which depends on time. And this perturbation can, for example, describe light. Okay, it might be the potential corresponding to an electromagnetic wave, which is going up to the electrons of your system. It can be something else. The important point here, even though I say it is a perturbation, it is not necessary that this is a weak perturbation. It can even be a very strong perturbation, because TD-DFT at no point, the Runge-Gross theorem says that this is valid only if perturbations are weak or if you're close to the ground state. So this external potential, which you're using to go push your system away from the ground state, in principle it can be very, very strong. No limit here. We are not trying to do linear response theory. Okay? And then one can solve, and this is done, has been done, as I said, by Birch for the first time. One simply propagates the Kohn-Sham orbitals, those of the ground state, which you know before you have had any perturbation. And you propagate each of them in time using the time-dependent Schrödinger equation. Here I've written it kind of in integral form. So you obtain the Kohn-Sham orbitals at the time t plus delta from those which you have at the time t, by applying a propagator e to the minus I Hamiltonian times the time step. So it looks more easy than it is. In fact, there are many kind of hidden difficulties here, because The Hamiltonian, as you know, depends on the density, as I've said. So in principle, you need to know the solution of this equation in order to write the equation. This is, again, the same DFT problem you always have with the self-consistency. But so let me just say here that this can be kept under control quite easily by taking a very small time step, by sometimes one goes back and forwards in time to find the right Hamiltonian to apply for each time step. So, but in principle, this is what is being done. You know the Cohen-Shum orbitals, the density at the time t. You go to one time step further by applying e to the minus I, the Hamiltonian, times the time step to the system. And in this way, you propagate everything in time and can then, at each moment in time, calculate all kinds of observables you are interested in. Okay? So as I said, this here is, it can be used for linear response, but it is not limited to doing linear response. These can be very strong excitations, as I will show you now. Okay? So in order to see kind of really how TD-DFT works and what TD-DFT is doing, I always like to show this kind of example where I take a very small molecule and I'm shooting a very strong laser pulse on top of this molecule. Okay? What I would like to show you in this, in the following few slides is in TD-DFT how a chemical bond is broken. And one can see it in real time using TD-DFT. Now the question is, how can I show you that the chemical bond breaks in a system? How can I kind of visualize a chemical bond? I could plot, show you a movie of the molecule, and then at each later time show you how the charge density evolves, for example. Okay, this is something natural. We always have access to the charge density, and looking at it, one could say, okay, we will see how a chemical bond breaks. But this is not a good idea to do, because it is quite difficult if you just look at the plot of a charge density to see, this is a triple bond, this is a double bond here, this kind of bond. It's not so easy looking at densities, even though one always thinks like it, but it's not so easy to see in a density image a chemical bond. What is much more useful to do it is looking at a function which is called the electron localization function. Some of you might know what this is. It is essentially a function which can be calculated if one knows the density at each point in space. And it is defined as a quantity. So this electron localization function is like the density. It's a scalar quantity defined at each point in space and obviously at each time, because since the density changes, this quantity will change. And you see the definition of it is 1 divided by 1 plus something squared. So this tells you it's a function which is always between 0 and 1. Okay? And what it really is these quantities d here, they tell you the probability to find a second electron at the point r if you imagine that one electron is already at this point in space. Okay? So you can imagine that if an electron is very much localized, then due to the Pauli principle, the probability to find a second electron there is very low. Okay? So the Pauli principle tells you if you have very localized electron, this d will be very low. If electrons are more like plane waves, completely delocalized, this here will get towards the value of a uniform electron gas. And in fact, this is kind of how this is defined. There is an approximation which tells you how one can approximate this probability if one knows only the density. But just keep in mind for what follows that if one knows the time-dependent density, one can calculate this time-dependent electron localization function. And I show you how it looks like. So this is the molecule we will be looking at. So it's C2H2, one carbon atom, the other carbon atom, hydrogen and hydrogen. And this plot here shows you this electron localization function between 0 and 1. And one sees very clearly that far away from the molecule, in fact, there are no electrons, and this function goes towards 0. In between the two carbons and here around the hydrogens, you see that this function goes towards 1, and this clearly here now indicates chemical bonds. Okay, this is in fact one of those bonds is what I would like to break later on. So very high electron localization function indicate you the presence of a chemical bond. In this picture, I've shown you a contour plot of this at 0.95, and you see here how it looks like. This is unfortunately, perhaps you can see it. So if one looks around it, you see that this has a symmetry, a rotational symmetry around the axis of the molecule here in between. So you can see in the ground state clearly that this here is a rotationally symmetric torus around the axis between the two atoms. And this is because you have here a triple bond, obviously, between these two carbons. So my goal is to destroy this triple bond now, and I try to destroy it by shooting a laser on this system, okay? So I will now take this system in the ground state, and as this external perturbing field, I will use a laser field where the electric field of the laser is polarized in the axis of the molecule, and I have chosen the frequency of the laser right now to get here this bond here destroyed, and I will show you what happens, okay? So what I'm applying, so this again is the molecule. This here is the external electric field. You see in the beginning it is very weak, then it is becoming stronger and stronger in intensity, and the frequency of this is something which I've chosen precisely to get this right. Now, obviously, it will not work at the very first moment I'm trying to do it. Let me try. I should have tried this right before here it is. Okay, so I show it in this way to you. Okay, so what is happening? I hope you can all see it. So you have this molecule here. In the beginning, the electric field is still very weak. And you see that you have kind of a linear response of your electronic cloud. It's just oscillating left and right. But now getting a stronger and stronger field, you remember I've shown you the intensity is growing. You see now non-linear effects. You see, for example, that pieces of electrons seem to be thrown out, so you see kind of ionization of this. And now look very closely at the triple bond, what is happening to this triple bond. See, it's getting broader, and then at some point, puff, now you see out of one torus, you've got two tori, okay? So what you have seen is in real time how this triple bond is going from a bonding towards an anti-bonding state, okay? So I like to show this, this example because it is kind of allowing one to understand what time-dependent DFT is really doing. One can follow in real time how electrons react to external perturbation. In this case, a very strong perturbation. You've seen the molecule got even ionized partly. And then you see here how one goes from one electronic state to the other, all in real time. So in principle, TD-DFT is like this. TD-DFT is propagating in time the electronic cloud and understanding what this is doing. So I go back to slide. Okay, so I like to show this always in an introduction of TD-DFT because one gets a flavor for it. However, as I've told you, this is not what normally people are using TD-DFT for. Normally, people are using TD-DFT calculations in order to calculate an optical spectrum. Okay, people want to make a link to experiments, and what an experimentator is doing, you have an unknown substance. In order to get its fingerprint, one is calculating spectroscopy. All kinds of spectroscopy, optical spectroscopy, electron loss spectroscopy, whatever. And what one would like to do with these methods, either with TD-DFT methods or with the many body perturbation theory methods, is to try to find out how the response spectra look like. So, and in this case for TD-DFT, how can we calculate in this framework a spectrum? So how can I get what is the absorption as a function of frequency? Now, when one talks about spectra, kind of one always means linear response. So let me start by writing some linear response equation. So now I'm assuming what I've not assumed before. Now I assume that the external perturbation is weak, okay? I want to assume that it is weak because I would like to write what happens to our system in a linear way, okay? So here I imagine, in a very general sense, that I'm applying an external weak perturbation at the time t prime and at the place r prime. And I'm assuming that this here leads to a change, obviously, in the charge density at your system. This change in the charge density, delta n, at some other place r and some later time t, okay? And saying that we are working now in linear response means that I'm writing here a linear relationship, okay? all higher orders. In this case, I will try to neglect, and I'm writing here the general susceptibility, which depends on R prime, and the time lag between these two things. So this is just saying I have a very weak perturbation, and I expect my system to react linearly to this external perturbation. Now, this here gives me a change in the charge density. If I have a change in the charge density, I can also calculate all kinds of other quantities. Here I'm now interested in how will the dipole of my system change due to the change in the charge density. This is calculated very easily. The dipole as a function of time can be calculated out of the change of the charge density simply by integrating over all space with the dipole operator. So here you have a position or the dipole operator, change in the charge density, and therefore one can obtain in principle the dipole as a function of time, knowing the external perturbation, and somehow the susceptibility will come in here. Let us now consider that here I do not plug in any kind of perturbation, but I plug in a perturbation which corresponds to an electric field. So an electric field, I can write it as the field strength, which I call E, times a dipole operator, okay? So in this kind of gauge, which I've chosen here for the electromagnetic potential which acts here, is that my perturbation is an electric field, its strength can vary in time, times the dipole operator 2. If I put in these two equations together, I can see that, so I take the previous equation here, I plug in for delta V, I plug in E times dipole operator at R prime, and then I'm calculating this here times the position operator to get the dipole. This will allow you to get the dipole as a function of E, and you see that you will get a dipole operator on the right at R prime, at the right of your susceptibility, and another dipole operator from this equation here to the left. So you have a dipole operator at R, a dipole operator at R prime, which are bracketing this susceptibility. And one ends up with the dipole as a function of time. The induced dipole, the linear response dipole at the time t, is linked to your electric field at the previous time t prime by, again, a quantity. So this here is dipole operator susceptibility times dipole operator integrated over all space. And this quantity alpha here is called the dipole susceptibility. Again, this is just writing linear response without anything more involved. Why am I writing this? Because this quantity here, the dipole susceptibility, is linked to what one is measuring in an optical absorption experiment. So if you're doing an optical absorption experiment, then what you are measuring, this quantity S of omega, the strength, the absorption strength as a function of frequency, is linked by some constant times the imaginary part of the Fourier transform of this quantity alpha. So our goal, if you would like to calculate a spectrum, should be somehow to get access to this quantity alpha, either of t or of omega. And once we know alpha of t, we could Fourier transform it to alpha of omega. We take the imaginary part, and we essentially can compare with what is measured experimentally. Okay? So I've been insisting on this dipole susceptibility because this is linked to what is measured in an experiment. And in fact, so I will now use time-dependent density function theory to calculate the dipole as a function of time. Then I simply Fourier transform it. I get the dipole as a function of omega, and I compare then the imaginary part of it with what we have. So here, this is a typical function of the dipole as a function of t. I've taken here, I think it's a benzene molecule, so a very easy example. And what I did is I used as external perturbation here a function which is always 0, except at time t0, it is a delta function in time. Okay? So you can imagine that my system is sitting in the ground state. At time t0, someone comes and gives the delta function a kick to the system. Why am I using here a delta function? Well, a delta function, if you Fourier transform it, it contains all frequencies. So if I give the system at t0 a kick like this, this means I'm exciting all frequencies equally at the same time. Okay? So one reason is using a delta function kick at t equals 0 excites all frequency of our system. The other reason is if you imagine that in this integral over time, here you have a delta function of time, then you have simply the dipole is equal to alpha, because the integral will go away. So by measuring the dipole, I directly obtain alpha of t. And this is what I need. I need alpha of t to Fourier transform it later. Okay? So what I'm doing here, at t equals 0, I'm giving this delta function kick to the system, and then I'm solving in real time the time-dependent Schrödinger equation for my Kohn-Sham orbitals, for my time-dependent Kohn-Sham orbitals, like it has been shown in the case before. But in the case before, I've had the external potential of a laser pulse. Here, I do not have this laser pulse, but only a delta kick at t equals 0. And what I obtain is something like this. So a very quick and heavy reaction in the very first part, and then you see over time there are all kinds of oscillations of the dipole of our system. So at each moment in time, I calculate the dipole, and I obtain this time function, d of t, the dipole as a function of time. I Fourier transform it. I take the imaginary part of the Fourier transform, and I get this function here. So the black line is what one obtains, in this case, from real-time TD-DFT as an absorption spectrum. Compared with the experiment, you see that one gets a very good coincidence with the experiment, because this main peak here coincides exactly, and you see kind of that one has a very nice agreement between very easy. So this is the simplest TD-DFT you can imagine, because it is simply adiabatic LDA. Okay, I use the LDA functional, the first one which existed. I use the adiabatic thing, so at each time I forget all the previous history of the density. And for a system like, for example, a benzene molecule, this works very well. Okay? So all I needed here is to do time-dependent propagation in time, a delta kick at t equals 0, and one can get an optical spectrum. So I could stop here and say this is how one uses time-dependent density functional theory. It would be true that I could stop here and that you could use TD-DFT to calculate spectra and so on. But if I stopped here, I would not have explained to you what people are really using and what people are really doing when they use TD-DFT, because it's not at all this which is being used. I said in the beginning that, so Runge and Gross, the theorem was developed in 1984. Then it was, I think, in 1996 that for the first time someone did a real-time propagation like the ones underlying this. So between 84 and 96, has no one used this? No. Everyone has been using time-dependent density functional theory in a different way, in the way which I will show you now. Okay? Because, so the idea is not to use time-dependent density functional theory in the real-time domain, but to stick with the linear response, as I've written it now, but to linearize all equations. So we are doing now kind of perturbation theory on top of time-dependent density functional theory. So unfortunately, I have to show you now a whole series of equations, but I try to make them as transparent and as non-boring as possible. Okay? So I'm trying now to linearize the time-dependent density functional theory equations in order not to solve the the time-dependent Schrödinger equation in real time, but to find some other equations. Let me show you how this is done. Okay? So first one calculates the ground state. Okay? Then again, like previously, we consider a perturbation, which is weak because we want to do linear response. So our perturbation is weak. And the perturbation is, in this case here, we imagine that it is characterized by a given frequency omega. So my perturbation is some operator times, if you want, e to the I omega t plus e to the minus I omega t. So only one frequency, a monochromatic perturbation, and a weak perturbation. I want to do linear response. So when I want to do linear response, then I say, okay, my Kohn-Sham orbitals at the time t will be the ground state Kohn-Sham, so the unperturbed Kohn-Sham orbital, plus some linear change. And I write this here in the following way. I write, therefore, that the time-dependent Kohn-Sham orbital is ground state plus a first-order change in the Kohn-Sham orbital times e to the I omega t, plus a different change of the same orbital times e to the minus I omega t. So I call this delta psi plus and delta psi minus, all here with a given frequency. This is an ansatz. Okay? I'm saying I have linear response, I have this kind of perturbation, and my orbitals will react only to linear order. Obviously, this is what will lie behind all this. If this is not valid, then the linear response ansatz we are doing is not valid. Okay? So I'm writing that my Kohn-Sham orbitals, they look like this here. obviously, if I knew delta psi plus and delta psi minus, I would have finished. Then I would know how the system reacts at all times. So the unknowns of what I would really like to find out is what is delta psi plus and delta psi minus. So given that I have written this kind of form here for the time-dependent Kohn-Sham orbitals, this means that obviously also now the charge density will change with time, because the charge density is the sum over the square moduli of these functions here, and therefore you will have a zero order and a first order term. If you are interested in the first order change of the charge density, this delta n, then you will find out that you have one term which goes again like e to the I omega t. I call this delta n plus, and one term which comes from this part here, which goes like e to the minus I omega t, and I call this delta n minus. Okay? So the response, the first order response in the density also will have two terms, delta n plus and delta n minus. It just comes from squaring this function here and making the sum of all this. So now, if the charge density changes in linear order, it tells us also that the Kohn-Sham potential will change in linear order. And which are the linear changes which we obtain in our Kohn-Sham potential? Well, on one hand, it is what I plug it in externally as a first order or as a weak perturbation, first of all. So this delta V is our external perturbation, which leads to a departure from the ground state. And then we will also have here, since the density has this frequency e to the I omega t, e to the minus I omega t, we'll also obtain a first order change in the Kohn-Sham potential, a delta psi plus and a delta psi minus, all written to linear order. So I'm just linearizing all kind of equations. These are the quantities which appear, and I'm putting it in the time-dependent Schrödinger equation. Okay? In the time-dependent Schrödinger equation, you have I d or dt psi, and for psi, I'm plugging in this ansatz, and then I have Kohn-Sham Hamiltonian times psi. In the Kohn-Sham Hamiltonian, I say this is the ground state Kohn-Sham Hamiltonian plus this linear change times the Kohn-Sham orbitals, which is ground state plus a first order change. Okay? So I obtain two parts on the right-hand side, the first order change in the Hamiltonian times the ground state orbitals, or the ground state Hamiltonian times the first order change in the orbitals. Okay? So I'm just taking all these here, plugging it into the time-dependent Schrödinger equation we have seen before, and then obtain, in fact, two equations. Why do I obtain two equations out of one single thing? Because I'm collecting terms, those which oscillate like e to the I omega t, those which oscillate like e to the minus I omega t, and this gives me two equations, and they are written here. So if you look at these equations, you see that they are clearly first-order equations, because each term here is first order. Here you see the unknown responses in the orbitals. Here you see ground state Hamiltonian, ground state Kohn-Sham energies times a first-order change in the Kohn-Sham orbitals. Here you see the first-order change in the Hamiltonian times the ground state Kohn-Sham orbitals. Okay? So this is clearly all first order. And in fact, one would have to solve this. So one would like, as I said, the unknowns which we would like to know is what is this delta psi plus and delta psi minus. This is what we really would like to know. Now, if you have two equations like this, I should also say, unfortunately, it doesn't look like this, but these two equations are coupled. Why are these two equations coupled? You see, it seems like this here is an equation for delta psi plus, this is for delta psi minus, so they do not look coupled, they seem independent. Where is the coupling? No, psi zero is not a coupling. It is in this part here, obviously, because the change in the Hamiltonian, which I call delta V, depends on the density. But the density you've seen is calculated from delta psi plus and delta psi minus. So you have these two equations, you need the solution of both of them to get the change in the charge density, and you need the change in the charge density to write this term here. Okay, so these two equations are coupled. So how can we try to solve them? Well, if you have something like this, it's always, or the most used thing is one is taking the sum and the difference of the two equations, and look what happens. Okay, so I'm taking once the sum of the two equations, then I'm taking the difference of the two equations, and this will obviously here, for example, lead to the fact that you have delta psi plus delta psi minus, and in some cases, like here, you have delta psi plus minus delta psi minus. Okay? So now I make a change of variables. Instead of the unknowns delta psi plus and delta psi minus, I call the unknown x and y. But the truth is this x and y is simply, again, it's kind of a change to each of the Kohn-Sham orbitals. X is the sum, Y is the difference. And if I write this equation here, so the sum and difference, and I massage a little bit this equation, then one ends up with something which looks quite easy, because what one obtains is omega, which is our frequency, minus some operator L, times this unknown X and Y, is on the right-hand side a given vector. Okay? Obviously, I have to explain this a little bit more, because it looks so different from the equation we have just seen before. So omega, the frequency, is just a number. What is this L operator? We call it L because it is in fact the Liouvillean of our system. And you see this Liouvillean, it is in this 2x2 world where I collect all the X unknowns and all the Y unknowns together. It is a 2x2 operator. And you see that, unfortunately, the operator one ends up with is a non-Hermitian operator, because this D is different from K, and therefore this Liouvillean is a non-Hermitian operator, which already tells you, things will be a little bit mathematically more complicated to solve than if you have a Hermitian operator there. So what are these D and K? Obviously, they are just the things which appeared in the previous equations. So D applied to a response orbital is simply applying the unperturbed Kohn-Sham Hamiltonian minus the unperturbed Kohn-Sham energy on an orbital. K is the same to an orbital plus something which involves the change in the potential. So this here is the so-called exchange correlation kernel. So this here tells you how the potential changes when you change the density. And so both of these things here, you see clearly, they are linear in the unknowns. Okay? So this is a linear equation which you end up with. It's a non-Hermitian linear equation, omega minus L times the unknown. And on the right-hand side, what you obtain here is linked to what we had in the previous slide here, the external perturbation acting on the ground state. Okay? So you know how you perturb your system because, for example, the perturbation might be light. In this case, it will be a dipole operator, this external perturbation, acting on all the ground state Kohn-Sham orbitals. This gives you this vector B. Okay? So now if you look at the form of these linearized time-dependent density function theory equations, what you discover, in fact, is this here looks a bit like so obviously it's linear, but then it is an eigenvalue equation. Imagine that you take away the external perturbation. Then you have omega times xy is L times xy. So it's really an eigenvalue equation. It's a non-Hermitian eigenvalue equation. And if you do not perturb your system externally, then the eigenfrequencies of this system here are the free oscillations of your system. And this is exactly what you would like to solve for. Okay? So if you are able to get the eigenvalues of L, and these are the omegas which solve this equation here, if you know these eigenvalues here, you know the eigenfrequencies, the excitations of your system. And then how strong in a given spectrum each of these eigenfrequencies will be excited, this will depend on the concrete excitation you're using here. For example, if you are perturbing your system with an electron which is flying by or with a photon which is coming in, this will change here the strength of each of the excitations. The eigenvalues of this operator L will give you the frequencies in which you can excite your system. Okay? So this is in principle writing time-dependent density function theory in linear response gives you this kind of complicated operator times the unknown xy is omega xy. So it's a non-Hermitian eigenvalue equation. Okay? So this is how one goes from a time-dependent Schrödinger equation towards this linear response equation. And this is the equations which everyone is solving. There are many very different ways how to solve it. In Gaussian, it's implemented differently from quantum espresso. So there are many ways how to solve it, but in principle, one is always solving kind of an eigenvalue equation. And you know, if you have a complicated operator, and numerically you want to solve for its eigenvalues, then one typically calculates first the lowest eigenvalue and eigenvector, then one calculates the second lowest one by keeping the solution orthogonal to the first one you have found. You get the second one. The third one you calculate it by keeping the solution orthogonal to the two you have already found, and then the lowest one you will get is the third one, and so on. So this kind of iterative solution of an equation like this, for getting the first eigenvalue, the second, and so on, this is what is done very often. And this here, so one solves this eigenvalue one, This is the standard way to proceed. So this goes also under the name of Casida's equation. Those of you here in the room who are part of this Assessma schools, they know Mr. Casida, who is a very nice guy, and he likes to come also to our teachings in Africa of density functional theory and so on. And he was the first one who has written, he has written the equations in a slightly different form, but essentially he was the first one who has written these equations. And this was a big breakthrough because the way he has written these equations was in a way that looks very much to what chemists already knew from configuration interaction theory. So from a completely different kind of theory, but kind of writing them in this way has shown everyone, TD-DFT is very similar to configuration interaction singlets, and then people started implementing it in the chemistry community. So he had a very important role in this. So the standard way to proceed, therefore, is to take this L operator and to solve, therefore, well, this is time independent, and then to calculate as many eigenvectors starting from the lowest frequency to the higher frequencies as you need, okay? And this is kind of really the standard way, which has a lot of advantages, but also a lot of disadvantages. Because, as I said, what you very often need is you would like to know what is the spectrum of your system, like the spectrum of benzene, which I've shown you just before. Very often one is not really interested in knowing all the eigenvectors which one needs to calculate here. You remember here you have this complicated operator, and you calculate it for each frequency also an eigenvector, because this is the only way how one can do this iteratively. In the vector, one is much less interested. One uses it, for example, to calculate the oscillator strength at that frequency, but generally one throws it away immediately after having used it. And this is something which one can perhaps do better, and I will try to show you how one can do this also differently. So I will not, I think, because of time, I will show you very much how one can do this iterative method which everyone is using. Just keep in mind, so trying to solve this huge L operator for first, second, and third eigenstate, you need to keep in the memory of your computer all the eigenvectors, because the next one you're looking for needs to stay orthogonal to those you have already found, okay? How it works is not so important, but I would like to show you what this means in the case of benzene. Okay, so this is again benzene. You remember we have seen the spectrum right before. And I'm now doing precisely this. I'm solving the benzene TD-DFT equations and calculating the eigenvectors, eigenvalues and corresponding eigenvectors of this L operator. And what you see here is, so these here are the eigenvalues of the Liouvillean in the case of benzene. So you have here frequency 0.3, 0.4, and so on. On the right here, on the right column for each of these frequencies, I give you the optical oscillator strength corresponding at that frequency. Okay, so for this I need the eigenvector. I calculated with this V operator we have seen before. I calculate how strongly at this excitation light will interact with it. And you see here, in fact, 10 to the minus 6, 10 to the minus 8. So essentially, you have no absorption at all at these frequencies here, and in fact, you do not see anything. This very strong peak which appears here, which is the first kind of discernible feature, which is about at 0.5, at the frequency 0.5, is the one which appears here. These are these two eigenstates at 1/2. I just now see that there is a mistake. So this is the energy in Rydberg, not in electron volt. I'm sorry for this. So at the energy 0.1/2, you have the first two strong absorption peaks. So even if you are interested in calculating only this part of the spectrum here, in this case, you would have to calculate 1, 2, 3, 4, 5, I don't know, 15 or so excitations until you arrive at the first ones which are optically active and design your system. And in this case, if you calculate all these frequencies here, your spectrum looks here like the red line. You have information only, obviously, up to the maximum energy you have afforded to calculate. And all the higher lying ones, you have no information about it. Often, this is good enough, because in some systems, you're only really interested in what is the lowest excitation, what is the second excitation. But even in as trivial a system as a benzene molecule, you see here that in energy, you do not get very far, and even just the first important one here might need to calculate you 15 excitations and so on. And now keep in mind, for each of them, as I said several times, now you need to keep in memory of your computer the eigenstate which corresponds to it, because for the next one, you need to keep it orthogonal to it. So very quickly, if you have a very large system, very quickly you run out of the possibility to treat this, because simply you will not have enough memory in your computer to do this. This is a problem which did not appear in the time propagation case. Remember, in the time propagation case, we only need to keep the size at each moment in time in the memory of your computer. We propagate this, and there is, in fact, in the time propagation case, no memory bottleneck, and you directly obtain information about all frequency out of one time propagation. However, there, you obtain the whole curve, but you do not obtain any information. Here, instead, if you would, for example, like to couple this with excited state molecular dynamics, you can do it, because here, having for this excitation peak also the eigenvector, you can calculate the derivative of the eigenvector with respect to nuclear displacements, as you can do molecular dynamics in the excited state. So there are advantages and disadvantages of all of these kind of things. Just so the usual way of dealing with TD-DFT by getting single frequencies and so on, it limits one, especially when the system becomes large, due to memory, to a rather small portion of the spectrum. So this is what I've just said. Now, I would like to explain to you a third way of solving these equations. This third way is important because it's the one which is implemented in Quantum Espresso, and you will be using it this afternoon. Okay? So it is a third way which is not a time propagation, but like in the time propagation way, it gives you access to the whole spectrum in one calculational shot. And it does not give you, like also the time information about the eigenvectors of the single excitation. Now, so how are we doing it? It is a way which is much more efficient than doing a time propagation, but in a sense, it gives you similar results. Remember this equation here, which I've shown you before. I said in order to know the optical absorption spectrum, we need access to what is the change in the dipole, and the key quantity was the dipole susceptibility alpha, which appears in this linear equation. Okay? So what we really need is a method which for the case of TD-DFT gives us efficiently what is a given expectation value of one given operator, in this case the dipole operator, as a function of time. Okay, so this I've said. So now consider more generally that not only the dipole, but we would like to calculate some operator A, and we would like to calculate what is the expectation value of some operator as a function of time. For the optical absorption, what we will be looking at is what is the dipole as a function of time, obviously all in linear response because we're interested in spectra. So the expectation value of some operator A is obviously the psi, A psi. If you write this in linear response, then you have either the delta psi to the left or to the right. Okay, so this is in linear response the change of some operator as a function of time. Okay, so here I'm just again writing linear response, and I'm writing that my time-dependent Kohn-Sham orbitals, they change only linearly in time, and so due to some perturbation, the induced change in the expectation value of A will have a form like this. What we need is the imaginary part of the Fourier transform of this operator, okay? Because the strength function was linked to the Fourier transform of the dipole, the induced dipole. So if we now, at this level here, we take the Fourier transform, then we obtain A of omega. And then what you obtain is here, for example, this where you have directly the ket, you have not delta psi of t, but you have delta psi of omega. And this is what we call the delta psi plus of omega. Here you have the complex conjugate involved. If you put this on the other side, when you Fourier transform this in time, you obtain a delta psi minus. So one obtains, in fact, that what we are interested in this, the Fourier transform of any observable, in our case, is the ground state Kohn-Sham orbitals times the operator times delta psi minus and delta psi plus, the unknown response functions which we would like to calculate. But remember that delta psi minus plus delta psi plus, which appears here, this is what we called x. Okay? So you have that the Fourier transform of the operator we are looking for is essentially unperturbed Kohn-Sham orbitals times the operator times the unknown response x. I can put these here together directly acting with A on these here, gives me a vector, and I can formally write this here is just a matrix element of this A times the unknown X. Why am I writing this? Because for the X, I have some equation which we have written down before. So this is just what I've already said before. But we know that this X is a solution to this equation. Omega minus L times XY is the external perturbation. Remember that this is the equation we have to solve because this here is our complicated Liouvillean which we try to solve for. So the X which appears here is the solution to this equation. Now I play a trick and I formally write that XY is omega minus L to the power minus 1 acting on this here. Okay? So I take this equation here saying that this Fourier transform of the observable which we are interested in is nothing but from the left I have the unperturbed Kohn-Sham orbitals where the operator is acting on it. Then I have omega minus L to the power minus 1, and then I have the external perturbation. Okay? So I've just rewritten the equations we have seen before. And if I would be able to calculate this object here, I had essentially my optical absorption at all frequencies which I would like. So what do we need to calculate? What we need to calculate is A acting on the unperturbed orbitals is trivial. Well, we know what A is. It's a dipole operator acting on the orbitals. Here we have the perturbation. This is also unperturbed orbitals times the perturbation. It's done immediately. And what we have here is therefore a matrix element of a complicated object. It's 1 over omega minus this complicated L operator. Now in mathematics, this is called the resolvent of an operator. So what we need is a matrix, one particular matrix element of the resolvent of this Liouvillean. Okay, so this is mathematically speaking what one needs in order to calculate an absorption spectrum is a matrix element of the resolvent of L. Now how can this be calculated? Because if I can calculate this efficiently, then I'm done. And in fact, there is a way how this can be calculated very efficiently, and this is what I would like to show you in the following. You remember L is a huge, complicated operator, and it is a non-Hermitian operator. Showing all the mathematical formalism in a talk, either you all fall asleep or I take 3 hours and so on. So it's quite complicated. So therefore, I will show you something a little bit easier. I will show you how one can calculate the a matrix element of an Hermitian operator. The fact that our operator is non-Hermitian, it adds complications later on, but I will not show you these complications. But the principle is exactly the same. Okay? So I will show you now, because it's quite easy, how one can calculate a diagonal matrix element of the resolvent of an Hermitian operator. And I hope you believe me that there is a way how one can calculate an off-diagonal matrix element of a non-Hermitian operator. Okay, so what one needs is a bit more complicated than what I show you, but it's in fact the same thing. So this H is some complicated but Hermitian operator, and I imagine I know this vector V of which I want to calculate the matrix element. So what one is doing is a so-called Lanczos chain. How is this done? The Lanczos chain is a series of vectors. The minus 1 vector is initialized as 0. The first vector is the vector which you would like to calculate the matrix element of, so is V. And then knowing the previous one calculates always the next vector with this kind of recurrence relation. So you obtain the next vector by applying the operator on the previous vector which you already know. With this A and B, you keep it orthogonal to the previous one and the before previous one. So it's something where, in fact, all you need to be able to do is apply H to the previous one, and essentially you obtain the next one. And then there are rules how you define these numbers, A and B, once you know these things. So why is this useful? Because you can show that if you create a series phi 0, phi 1, phi 2, phi 3, phi 4, and so on, they will all stay orthonormal. You can show it if you take these equations. You have a series of vectors which stay orthonormal. And the nice thing is if you write your complicated operator in the basis which you have created in this way, so in the basis phi 1, phi 2, phi 3, phi 4, this Hamiltonian is a 3-diagonal, not Hamiltonian, this operator is a 3-diagonal operator. So it's not diagonal, but it has non-zero elements only on the diagonal and directly next to the diagonal. So you can see it here, in fact, this H here, it links phi n plus 1 and phi n. and phi n minus 1. It does not link phi n with the phi n plus 2 or phi n plus 3 or phi n minus 2. So it links only the neighboring elements one to the other. This has been known for a very long time, these kind of Lanczos chains, which one can define in this way. Keep in mind that, so in order to do this here there is a frequency omega, but this whole chain is independent of frequency. So you do not need to, like in the Casida case, calculate something different for each eigenvalue. No, you do such a chain, and this is the time-consuming part of what you have to do. This Lanczos chain here is completely independent of the frequency, and it gives you a representation, a basis in which this operator H is tridiagonal. So if you now write in this basis the operator H, you see that the A's are these numbers which appear on the diagonal, and directly next to the diagonal you have the B's, and all other numbers are 0. So this is what you gain. You have some complicated operator. Thanks to these Lanczos chains, you write it in a 3-diagonal way. This whole procedure is independent of frequency. Before I've said memory is a problem if you have to keep too many of these vectors in memory. Here you need to keep in memory only 3. You only need to keep in memory n minus 1, n, and then the next one. Then you can forget the previous vectors, which is another big advantage of a Lanczos chain. In memory, you have always only these 3 vectors. You do not need to keep in memory all the previous stuff. And you obtain, so the crucial point are these numbers a and b, which you obtain, and you go here in principle as far as the dimension of your problem, or you go as far as you need with this chain. Why is it useful? Well, you have your operator looks like this. Therefore, omega minus your operator is also 3-diagonal because it's simply omega minus, and then you have this 3-diagonal stuff. And remember, now you need a matrix element of the inverse of this, and you can very easily show that if you have a 3-diagonal operator, the inverse and the matrix element which corresponds to this angle here is given simply by a continued fraction. So you obtain that this here, the matrix element of omega minus h, is 1 divided by omega minus and so on. So you need to know only these numbers a and b, and you obtain what you were set off to do for any frequency simply by solving a continued fraction expression. Okay? So now believe me that one can do the same if H is not Hermitian. So we do the same for this complicated operator L. It is non-Hermitian, but you do in principle exactly the same story. You obtain for L a 3-diagonal representation. Instead of the numbers A and B, you will have A, B, and C numbers because it's non-Hermitian. So therefore, this upper diagonal will be different from these numbers here. But so in principle, you have numbers A, B, and C. And you obtain also a continued fraction, which gives you for any value of omega, what is the expectation value of your in this case, dipole. Okay? So we want to calculate, therefore, this quantity here. We have said the frequency, the Fourier transform of the dipole is the off-diagonal matrix element of omega minus L to the minus 1. We write L in a 3-diagonal way, thanks to a Lanczos recursion. And then we obtain this dipole here with a continued fraction. And this works, in fact, very well. Let me now show you some pictures of how this works. So we do this, yes? Yeah, this is exactly what comes next. So in the next few slides, I will try to answer this question. Okay? So I start with the vectors where I start is clear. It's the ones which correspond to the perturbation I have. But in principle, this goes until you have reached the dimension of your problem, which in our case, for all practical purposes, is nearly infinite because the system is so large. So we start here. So what we do is we start this continued fraction calculation, and we stop somewhere just because we don't have more time, and we look what happens. And then we continue doing some more, and we compare until one achieves conversion. So the short answer is one goes until one is converged. And now I will try to show you how convergence goes. Again, this is benzene. You see here you have this main peak, and you see as you have only, so in this case, I used 1,000 iterations. It's a very nice convergence already at this first peak, but then at higher energies you have some completely unrealistic oscillations. You go to the red curve, so you take a longer chain and therefore do use more states in your continued fraction. And this here is already much better, up to higher energies. And then as you increase and increase the number of iterations, at a certain point, your spectrum is converged to the exact spectrum, which you can see here. This does not only work for benzene, but for all kinds of systems. Here you see what happens to, for example, a C60 molecule also. The convergence always nicely starts where you're most interested at low frequencies, and then convergence becomes better and better, also at higher energies in your spectrum. One can do this also with ultra-soft potential. It's not so important. But now comes, I would like to mention also a trick which we have been using. Okay? So we, as I said, what is still expensive is doing this Lanczos iteration, which gives you these A, B, and C coefficients in your tree-diagonal representation. This is expensive, and you like to do as little of them as possible. So the kind of first approach is you do as many as you can afford. You put them in the continued fraction, and then you put 0 when you do not know what the numbers are anymore. But now let's have a look at how these coefficients look like. So this is one of the 3 coefficients as a function of the Lanczos iteration. And you see that these coefficients, they are kind of, as a function of the iteration, they are spread around some values, but they are not anything. They are kind of clearly here clustered around, for example, 13. So they are not 150, 0 or something, but they are clustered around some mean value. If I plot in red and black differently the odd and even coefficients, I even see that kind of the even ones seem to be clustered around one value, the odd ones around the other value with a rather small spread. So the idea to accelerate convergence even more in these calculations is that you calculate exactly a given number of coefficients, and then once you cannot afford to calculate anymore, you approximate the rest of your coefficients by the average value you've had before. And we choose a different average value for even coefficients than for odd coefficients. Okay? So we calculate these coefficients expensively up to a given number. This number still has to be defined by convergence test up to where you have to go with these calculations. And then in the continued fraction, we continue up to, I don't know, 10,000 or 20,000, whatever you want, with the average value of what has happened before. This is something which accelerates greatly convergence. So we call this a terminator. So you have the nothing to do with Schwarzenegger. It is a continued fraction which you have to terminate somehow, and we terminate it by putting average values there. So if you put just 0, so we have no terminator, then we have what is shown here to the left. You see with 500 iterations, the spectrum looks like this. And then with more and more iterations, you see that also the higher energies you start to converge, and you are converged essentially at 2,500 iterations. If you use this terminator, then you are essentially, with 500 iterations, you're already very much converged everywhere. Okay, so using this trick of terminating the continued fraction with the extrapolation of your numbers by the average value is something which is very, very useful. And so let me show you a kind of a more complicated system. This here is a squarane molecule, and also here one gets the same kind of behavior with a number of Lanczos steps which one needs to do. Something which I told you one cannot, but does, yes? So this average value which is there, we were able to show that this is related to what is the kinetic energy cutoff. Because at high energies, your spectrum is essentially, not completely, but it is very much determined by what does the kinetic energy, because that is not bound, and at high energies, you have more or less kinetic energy. So if you use plane waves up to given kinetic energy cutoff, then this here will determine the average value which you obtain. Okay? So typically, if you have, I don't know, 50 Rydberg cutoff, then the average value will be around 25. This is what one, in fact, one can show. Now, the difference between odd and even ones, this is related to the band gap of your system. One can also show this. Okay, so it's a bit complicated. If you write how the density of states looks, then you find out that more or less the average value is given by the kinetic energy cutoff, and the spread between those is linked to the gap of your system. So this is kind of in 2 sentences what it is. So now, before concluding, I just wanted to tell you, I said that this approach is very much like the time propagation, in the sense that we obtain the whole spectrum, but we do not obtain the eigenvectors of each excitation, so we do not have this vector at our disposal to analyze it. Okay? Normally, in the Casida approach, you have the vector, and you can analyze, this is mainly a HOMO-LUMO transition, or this is, I don't know, HOMO -2 to LUMO +5. These kind of analysis can be easily done if you have them at your disposal. In this approach, like in the time propagation, you do not have this. But you can do something more. Because as you have seen, the way this all has been derived is that we can calculate any observable in linear response. Okay? And we have been concentrated on the dipole observable because that defines our oscillator strength and the spectrum. But in principle, we can calculate also as an observable the charge density. So what one can do is, and this is, we are doing this sometimes, if we see that our spectrum has an interesting feature, for example, a peak at a given frequency, which we would like to understand what it is, then we focus on this particular frequency and we calculate the charge density response with a Lanczos chain like here. Okay? So you can do the same in this case. We have here obtained a spectrum of this system, and we said, okay, I would like to know this excitation here in space, how is it related to the structure of my molecule? Okay. I can do this, and the result which one obtains in this case here is this. This is a picture of the charge density response precisely at this frequency. Okay. So here you can just see that this is in fact the response, and therefore since this is the first peak, it's very likely to be mainly HOMO-LUMO, is delocalized over the whole molecule. But there are cases where these kind of properties give you important insight. For example, where in a complicated system is the absorption taking place? Okay? Is it taking place in some optically active region, or is it happening at the interface with the solvent, and so on? So looking at the response charge density can sometimes be very interesting and give you additional insight into this system. So this is just to say that this whole Lanczos and recursive iterations which one can use in TD-DFT and which are implemented in quantum espresso, they are not limited to optical absorption. In fact, so this afternoon there will be the hands-on sessions where you will see how all this is done in quantum espresso, and there will be so two things I would like to say about that. Obviously, the most important application is optical absorption, the one which I've shown here. But TD-DFT can do any kind of neutral excitations. So one other kind of neutral excitation is electron energy loss spectroscopy. So where it's not a photon which comes onto your system, but where an electron with a given wave vector is flying by. The electron is not getting stuck in the system, but it is perturbing your electronic system. This is called an electron energy loss spectrum. This is a neutral excitation, and is something which is amendable to calculations by time-dependent DFT, and this is also implemented in in quantum espresso. So you can use quantum espresso for optical absorption, but also for EELS spectroscopy. The other thing which I want to say is about this afternoon. This afternoon, you will see, in fact, various approaches to this, and the first one is calculating electronic excitations without the corrections due to TD-DFT. Okay? So where you have just the Kohn-Sham orbitals, and then you are wondering what spectrum results from just transitions between these Kohn-Sham orbitals. There's also a code included which is called the epsilon code, and you will first do on a test system with this, the absorption spectrum, and then with this Lanczos scheme. And I hope that if you really do it, it will become a bit more clear how this is done in practice with this Lanczos recursions. Okay, so I think I have finished what I wanted to say, and I'm anyway over time. So I've shown you, in fact, that in which sense TD-DFT is a formally exact extension, very similar to the density function theory for the ground state. One can solve it either in real time or in a linear response. And yes, and then this is something, obviously, I have not done any of this alone. So the things which are the applications which I've shown you have been done also together with Filippo De Angelis. The person really involved in developing the idea with the Lanczos and so on is Stefano Baroni, who I've also seen last week already many times. And then there's a whole series, Brent Walker, Rocca, Baris, Arrigo, and so on. And in fact, the whole quantum espresso community which have their part in having developed this. Okay? So I'm happy to answer any questions, either now or at coffee, as you want. So questions?